Welcome back. I'm Professor Xiao Ma. In this video, I will demonstrate and explain a specific hands-on problem. This problem is likely in your homework. But keep in mind that for demonstration, I will use example datasets about predicting credit card customer default outcome. When you do your homework, the dataset is different. Make sure you adapt the codes for the homework. Now let's get started. In this particular demonstration, I will actually use fewer packages than the previous recent demonstration about multi-layer perceptron model. Notice I use a random state 30, NumPy random seed 30. I moved the useful function to the top because I will not break down for loop processes. We will put the for loop process inside one cell. I will use these two utility custom functions. One is for calculating the sigmoid activation. The other is to calculate forward propagation in one step. I use 4 dataset files for this demonstration. The dataset has already been splitted into train and test sets, and the dataset has already been pre-processed and separated the target from the input variables. So 2 data files for the train set, 2 data files for the test set. Within each, 1 data file for the Y data only, the other data file for the X data only. Therefore, there is no ID column. Read in the Y data and X data. Do some sanity check in terms of dimensions. Print the first 5 rows of Y data for the train and test set. Observe that for the train set, only the row with index 3 has value 1. Other values are all 0. For the test set, the target variable all have label 0 for the first 5 rows. This is mostly because customer default rate is only 20%, so the majority of the customers did not default. Print the information of the X variables using the train set. These information should be mostly similar between the train and test set for the input data. Print the descriptive statistics of the input data set for the train and test. They will mostly be similar. In printing these descriptive statistics, in order to show more columns, I converted the values to NumPy first. The table will look more compact after stripping away the metadata, including the column headers. Recall from the previous video about multi-layer perceptron model, in calculating the model performance, such as accuracy, you still need a flag variable format of the target variable. Here, you do not have that. You only have the one-hot encoded Y data, which has 2 columns, one for the label of 0 and the other for the label of 1. Here I show an alternative method of getting the flag variable for the target besides the method that was demonstrated in the previous video. Here I will use the one-hot encoded format of the Y data to get the flag variable for the target. I use NumPy argmax. This works because in each row of the Y data, the label of the value that is greater inside that row will be flagged. Finally, before modeling, I will convert both the Y data and X data, including the train and test set, in total 4 data frames, convert them into NumPy array, which is similar to matrix. Now let's add regularization into the implementation of MLP model. To refresh your minds, to add L2 regularization, the initialization step needs to be slightly modified. You will need an additional variable or parameter, which is a hyperparameter. It's the L2 regularization parameter. In theory, it's called lambda. Here, I will give it a name, L2 param, similarly to when I implemented the logistic regression. Here, I will choose a much smaller L2 param, which is 0.01. 1 to the e minus 2 is 0.01. The reason I choose a smaller L2 param is because the data set here is not as noisy. This is a knowledge I have about the data set. In a real-world project, you probably need to try a few things with a wide range to see what is the optimal value for the regularization parameter. What's also different is the epochs. I reduced the number to 400 because with regularization, the model will quickly stabilize, so I don't need that much of training time. Other than these, everything else is the same, so let's run this. Observe that with the same random state value as previously, you get the same random draw for the initial values of the weights and the biases. Now let's look at specifically how to modify the code to add the L2 regularization. Here is to refresh your memory. In the previous video, we implemented a multi-layer perceptron model without regularization. The codes look like this. So, what do you have to change about the codes of implementing the model in order to add the regularization? Not much, actually. You may be surprised. Adding regularization to the MLP implementation codes is quite straightforward once you have understood how the processes have changed from the high level. Let's look at the cheat sheet for the implementation timeline for a second. This is an updated cheat sheet based on the basic version of the MLP. Now it's not the basic version anymore. It has additions and notes about implementing regularization. The changes and modifications are indicated by blue circles or purple notes. As you can see here, the changes are minimal. There is one change in initialization, which I talked about just now. There is a critical change that has to be made in the backprop stage, particularly in calculating the gradient of the weight matrix only. This includes the weight matrix of the output layer as well as the weight matrix of the input layer. And that's it. In backprop, that's the only change that has to be made. And finally, within the loop, in calculating the cost function, an additional term, or two additional terms actually, has to be added. One corresponds to the output layer weight matrix, and then the other corresponds to the hidden layer weight matrix. And that's it. That's all the changes that have to be made. So let's look at them one by one, beginning with modifying the gradient function. For the gradient function in the output layer, only the gradient for the weight matrix has to be updated with L2 regularization. Keep in mind that we do not regularize the bias weights, so we leave that alone because the bias weights almost has nothing to do with overfitting. The additional term to add to the gradient function of the output layer weight matrix is this. And the reason we add this term is because the gradient is a partial derivative of the cost function with respect to the weight matrix of the output layer. After applying the partial derivative of the additional part, which is the L2 regularization, this is what's left to be added to the gradient descent. It's the multiplication between lambda, a scalar, the L2 prom, with the weight matrix of the output layer. It's very straightforward. So in Python implementation, you simply multiply the L2 prom parameter or variable with the weight matrix of the output layer. It's also a matrix that has the same dimension as weight matrix of the output layer. Dimension is d by t. So that's good. And we also need to regularize the hidden layer weight matrix. So the hidden layer weight matrix also has an additional term. It follows the same structure, but the only thing that's different from the output layer is the actual weight matrix that is being added. Here, it's the weight matrix of the hidden layer. And this change is also noted in the cheat sheet. You can see here, the gradient function for the weight matrix of the hidden layer is to add multiplication between lambda and the weight of the hidden layer. In Python, it's multiplying the L2 prom with the hidden layer weight matrix. So that's the only changes in the backprop process. The other change inside the loop is the cost function. The original part of the cost function will end here. It's a binary cross entropy of the binary outcome. The additional term, which is added to the cost function, have two components. Each one corresponds to each of the two weight matrices that we would like to regularize. Now, in theory, for the cost function, the additional terms can be found here. It is basically the sum of the squared weight matrices of the hidden and the output layer. Each of these are a matrix of different dimensions. You will like to take the square of each of the elements of those matrices and add all the elements up. That's why you have two summation processes. Although the formula looks daunting, Python implementation is quite straightforward. You raise to the power of 2 for every element of the weight matrices. Double S0 is raised to the power of 2. And then you simply use NumPy.sum, which will sum across the rows as well as across the columns. So in one step, it calculates the grand sum of all the elements after taking the square of each of the elements. Do the same for the output and hidden layer, and there you go. Let's look at the Python implementation. That's exactly indicated in the cheat sheet. So by this point, you have successfully added the codes that's needed to be modified to add the L2 regularization to MLP. Now let's run this. Let's see how many seconds it needs to train. Notice that this time we have a fewer number of epochs to train. We need to train 400 epochs only. Let's run this. Training finished, only took 3 seconds. I will print out the value of the output layer weight matrix just to take a look. Recall that dimension of the output layer weight matrix is 7 by 2. 7 corresponds to the number of units in the hidden layer, and 2 corresponds to the number of units in the output layer, which also correspond to the number of labels in the Y data. Compare the values that you got and make sure that they are the same. Now let's examine model performances. The model is trained for 400 epochs with regularization on the training set. Take a look at the cost and accuracy. Accuracy is 92%, not bad. You may wonder why the cost value is so small, 0.56. This is because of a change that I implemented here, which is slightly different from the demonstration in the video of the basic version of the MLP model. The difference is because of this. I calculated cost as the average cost per observation, instead of calculating the total cost across all the observations. So if you compare the codes of calculating the cost, you will notice something is changed. This part is the same without the regularization, but this time I updated the cost by dividing it by the number n, which is the number of training examples. So in the end, the cost value is updated to be the average cost. Doing this has an advantage of being able to compare the cost curve and cost value across different training that involves different number of training examples, so that you're comparing per observation or average cost every time. And the average cost is comparable because it has been normalized by the number of training examples. Let's come back to the evaluation of the model. Now, I would like to examine the training set curve because I have saved the average cost value as well as the accuracy value in every epoch. These graphs should look quite similar to the graphs that are shown in the previous demonstration, which is the basic version of the MLP model. But there should be some slight differences because of implementing the L2 regularization. These are the same codes as used before. Let's take a look. Run this. Here are the graphs. For easier comparisons, I have taken a screenshot of the results curves from the previous demonstration and put it on the upper right corner, and you can see the graphs generated from the current implementation in the lower left corner. The immediate impression is that the two curves, as with the cost and accuracy, look similar across the two implementations, but there are some noticeable differences. The first is the scale of the cost. In the previous implementation, I did not calculate average cost, but the total cost. So that's why the scale is in the thousands. But here, the scale is in the decimal. but the shape of the curve line should not be affected by that difference. Another difference is the length of the training time. Previously, I trained for 1,000 epochs, now only trained for 400 epochs. So the portion of the previous curves that is until the 400 epochs should be used to compare with the current graphs. Across the two implementations, you find the same pattern of oscillating accuracy. It seems to be the case that regularization doesn't really fix this oscillation problem. You observe the same in both implementations. Recall what regularization does. Regularization mainly adjusts the penalty structure and prevents the model from learning very large or extreme parameters such as the weight matrices, so that the model is not overly fitted to the training set. Because the training set in this demonstration is not as noisy, regularization did not have a large impact on how the model learned from the data. But also keep in mind that I use a smaller L2 prom. So the fact that you don't notice much difference doesn't mean that regularization has no effect. It simply has a very small effect. And finally, let's take a look at the performance evaluation on the test set. We will use a current weight to perform forward prop one time and make classifications. After that, I will calculate the accuracy based on a flag version of the y variable in the test set and compare that with the predictions of the model. Let's run this. The test set accuracy is also 92%, very close to the train set accuracy, which means there is not much overfitting shown in the results. The truth about this dataset is that with a sufficiently trained and regularized model, the model should be able to achieve close to 93% of the accuracy rate. So the bias is also low. The current model is quite accurate and has a low bias. This concludes the demonstration. In this demonstration, I highlighted how to take the code of implementing the basic version of the multi-layer perceptron with 3 layers and how to add the L2 regularization to the MLP model. I trained the model with a new set of datasets which are essentially the same dataset, but it is already splitted and pre-processed before reading the data. I hope you have enjoyed this video. See you next time.